Please take it away.
Thanks, Andrew. Good afternoon. I hope you can all hear me clearly. So I'm giving this talk on behalf of Rachel Webster and the rest of the Murchison Wide Field Array Epoch of Reionisation project team. So for those of you who might be new to Astro 3D, just a reminder that the Murchison Wide Field Array, or the MWA, is a low frequency radio telescope in the Murchison region, and its centre is located not too far from ASCAP. This lovely image that you're seeing on the screen here is a photo of some of the 256 individual tiles that sit on the ground in the Murchison, spread over an area of diameter about 5 kilometres. And the interferometer forms baselines between each of these tiles. Each of these tiles is made from these dual polarisation dipoles. The MWA is a general purpose low frequency radio telescope. It has a lot of different science goals, but one of the primary ones is exploring the 21 centimetre signal from the epoch of reionisation. And so that's from redshifts of about 5 through to about 15. And we use a lot of these short baselines that you can see here to get the angular scales on the sky of interest to us for the EoR. So here's the MWA EoR members as they currently stand, including some former members, students who've moved on. We're mostly based at the Curtin and the Melbourne nodes, but we have a few affiliates internationally as well and in other national nodes. There have been about 35 collaboration papers so far within Astro 3D, so we've been very productive, and I'll highlight just a few of those today. These three individuals are our finishing or completed students. So Ronnie Joseph and Bella Nazaruddin have now finished and they've moved on to postdocs overseas. And Masa Rahimi, who you can see on the bottom here, has actually just submitted her thesis at the University of Melbourne. So that's very exciting for her. So globally, EoR and cosmic dawn science with low frequency radio telescopes is a very sort of international research theme. And you can see here I've highlighted a number of the experiments that have existed in the past, currently exist or will exist soon, that are trying to explore this era from redshift 6 up to about 25. Now, of course, we're interested here in the MWA, which is based in the Murchison in Western Australia, and the future square kilometre array will have its core about 10 kilometres from the current MWA. The ones I've highlighted in purple here, so LOFAR, the low frequency array in the Netherlands, HERA, the hydrogen epoch of reionisation array in South Africa, and the MWA here in Australia are really the three telescopes that are currently publishing competitive results, trying to explore the epoch of reionisation era from about redshift 6 to 10, rather than pushing unnecessarily into the higher redshifts. And so those are the ones I'm going to focus most on today, because these are the ones who are really actively pursuing this field. So 21 centimetre observations span a number of different redshifts, and in the blue box here you can see reionisation, which is what we've principally been pursuing with the MWA, and also with HERA and LOFAR. The green and red boxes are in the epoch of X-ray heating and pushing towards the cosmic dawn, and that's where the global signal experiments such as EDGES are currently operating. But we're also seeing some of the other telescopes with their low frequency antennas starting to push into those cosmic dawn frequencies as well. There's a gap in the middle at the moment where we don't have many observations. And that's because it's a sort of a difficult piece of parameter space where the signal is harder to get at, the signal is weaker and sort of less interesting. And so you find that people are either going for this big absorption trough here, which is a larger signal, or the lower redshifts in the epoch of reionisation, where we can actually have a sky that is relatively cooler, and the experiment from a relative point of view is more straightforward. So a lot of the heavy lifting work for the MWA EoR project is not in actually producing the 21 centimetre signal itself, but in understanding everything that happens to our signal from when it leaves the high redshift universe to when it gets to us. And so there's a lot of work from the individuals that you can see on this slide here to understand our sky model, and that's point sources, extended sources, and also the very large scale emission. And Mike will talk about that briefly in a sprint talk coming up. The signal has to come through the ionosphere, and that distorts our wavefront, and we need to understand what that does, and Karaoke will talk about that. We need to understand the instrument exquisitely well. And Aman is going to talk about that in just a moment as well, but there's a lot of work that's gone on in that area. But also how we do our analysis, how we actually take the data that we receive and try and sift through it to understand what we are and are not observing is a really important piece of the puzzle. And so there's a lot of work, excuse me, that's gone on in that space as well. And on the bottom here, you can see the full end-to-end simulation. So this is something that Jack Lyon is working on here at Curtin. This helps us to model the entire signal chain from everything we receive from the sky all the way through our instrument, through our analysis, so that we can really understand what we are and are not measuring. So the output of all of that heavy lifting, which is really the work that we spend most of our time doing, is the EoR Power Spectrum. And so the Power Spectrum gives us a measure of the amount of signal on a given scale on the sky. And we use this because it's a nice way of being able to integrate a lot of information together to be able to get a detection of this very weak signal. Given our models, we understand that at most redshifts, we expect that the distribution of these brightness temperature fluctuations are mostly Gaussian, and therefore the power spectrum, or the variance of that distribution, does provide most of that astrophysical information. And so that's the reason why we aim for it. So a couple of years ago, Wenyang Lee, who was at Brown University, part of the international collaboration, and Nicole Barry, who was at the University of Melbourne and now is at Curtin, undertook some new analysis of old data and also some new analysis of new data, and was able to really push down our upper limits based on new techniques, new calibration, all of that heavy lifting work paying off to give us the most competitive results in the field to date. And then last year we published a much larger piece of data. This was something that looked at our data over multiple years and was able to produce the deepest limits at what I would call relatively low redshifts when you're talking about EoR and cosmic dawn. So redshift 6.5 and 6.8. And these, together with Wenyang's and Nicole's limits, are some of the most competitive limits in the field, and helps us to understand that part of the piece of the puzzle of the full history of the universe. And then most recently, new results out this year from the collaboration. Shintaro Yoshiura, who's an affiliate member, actually looked in the epoch of X-ray heating, and so redshift 15.2, so this is now much higher redshift. Our data here are really horrible. We see the whole sky. It's very, very complicated, a very complicated instrument and a very active ionosphere, and he was able to produce some very interesting limits at those redshifts. And so pushing the MWA observations beyond what we were doing before. And Masa Rahimi, who has just submitted her thesis, as I mentioned, she has a paper under review at the moment, which looks at one of our other fields with just 14 hours of data. And again, with that improved analysis, has really competitive limits. In fact, they're more competitive than the ones we'd produced a year before with nearly 10 times as much data. And so you can see how that's moving us forward, all of that work that's been done. Now, one of the new things, probably new things in the last 2 to 3 years that we weren't able to see before is the marriage of the observation and the theory. So previously, the results out of the experiments were just not interesting enough for the theorists for them to apply their models to and actually be able to constrain the astrophysics of the IGM at those early times. But now the experiments are getting to a point where we can actually put these models forward. This is some work by Brad Gregg. I know in the next talk, Yushang is going to talk about a similar type of analysis on the HERA results, but this is a full MCMC analysis where effectively what you're able to do, if you look at the bottom left here, is you can rule out astrophysical models that exceed the upper limit power spectra that we produced from the MWA. And they typically are models where we have the IGM very, very cold, so there hasn't been any heating of the IGM. You get a very a high amplitude power spectrum in that case. But there are some other models that you can rule out. And there are models of the early universe that the MWA results can rule out that other traces of the early universe have not been able to rule out to date. So I also mentioned that there's some more work going on with the other telescopes into the epoch of X-ray heating. And so the MWA is also pushing into this space, but now we're expanding those observations to be able to not just target the EoR, but actually move to those low frequencies or those higher redshifts. So I just want to talk briefly about LOFAR and HERA because they're the two other competitor instruments and experiments. LOFAR is like the MWA. Yeah, it's in the Northern Hemisphere. It's made from these individual aperture array tiles, and it's a general purpose instrument. And so it suffers from a lot of the systematic problems that we have with the MWA. Nonetheless, in the same week that we published results last year, they published some very competitive limits at redshift 9.1. So this is now adding another little piece of the puzzle. MWA is adding one piece of the puzzle, LOFAR is adding a different piece of the puzzle. And so this is a really nice story internationally as for how we're pushing this field forward.
A minute.
Oh, thank you. Over the last couple of weeks, HERA also produced some results. Now, HERA is very different. It is a telescope that is designed to do this experiment and this experiment alone. And so it's designed in a very different way. Their methodology and their analysis is very, very different from ours. And they are able to produce a very, very clean signal chain that doesn't have some of the spectral characteristics that we have in our signal chain. And so their results are actually extremely interesting. If I just sort of, and their results are at redshift 7.9 and 10.4. So again, fitting in different pieces of the puzzle for this full evolution of the universe. What's really interesting is that their system is designed to be very, very clean, and they're getting 10 to the 9 in dynamic range in their power spectra. We're getting about 10 to the 7 at the moment. And so that's a lot of the work that we're doing is to increase that dynamic range and really be able to push down to the sort of things we're seeing out of HERA. So just to take some Astro 3D context for this, we don't just work within our own project, of course, and we do a lot of work with Genesis and also a little bit now with Galaxy Evolution. And so this is some work by Bala Nazaruddin. So this is some work that she did to try to bring the theory together with the observation and have a really realistic and physical end-to-end model of what our telescopes actually observe. And she was able to show some really interesting results that can be used now and applied to the upcoming Genesis cubes that we're looking forward to being able to use. And on the Galaxy Evolution side, we've also been able to do some work where we've looked at MWA signals around Lyman alpha emitters that have been observed in the optical. And so I know Emma's going to talk a little bit about Lyman alpha. We're starting to get to the point with MWA where our results are deep enough that we can start matching up with other traces and not just having radio be a siloed sort of research thing. Okay, so in the last minute, let me just talk about where we're going next. So MWA very excitedly is moving into phase 3. That means we have a brand new correlator that we're about to work with that will give us a cleaner signal. And more exciting for us, we're going to be getting new digital receivers in the future. And those receivers will clean up our signal chain and get rid of all of these horrible harmonics that we have in our EoR Power Spectrum, just because the instrument itself has a lot of spectral structure to it. We're also working on new pipelines. So Bart Pindor and Chris Jordan here are working on our current calibration software, but also the next generation of software, and that will move more and more towards SKA. So Elaine mentioned OzSRC yesterday. We're working with OzSRC to get those pipelines really efficient and effective so we can move towards MWA phase 3 and the SKA. So outlook for Astro 3D. MWA is continuing to play a world-leading role in EoR measurements, and HERA and LOFAR are our competitors, friendly ones. It's not a race, but of course it is a race in a friendly way. We're preparing for MWACS and new receivers and working towards that SKA transition with OzSRC. And for Astro 3D, we're really moving beyond the power spectrum and looking at other statistics and some cross-tracer analyses that have been enabled by our increased sensitivity, our increased performance of the telescope. And excitedly, observation meets theory. So increased opportunities for collaboration, particularly with Genesis and Galaxy Evolution, but I'm very open to collaboration with other projects if we can think of some projects together. And as always, really exciting results from students across the collaboration, and I'm looking forward to that continuing. Thank you very much.